Welcome everyone to our first post-spring break colloquium, unfortunately. Our colloquium last week, you may recall, was canceled because our speaker actually had tested positive for COVID and was pretty sick. She's doing much better now. Our speaker today is Nicolas Scepi, who is here at GILA. Nico got his PhD at the Institute of Planetology and Astrophysics in Grenoble, in France. Sorry, I didn't try to give the actual original, where he got his PhD in 2019, and where he worked on accretion disks in dwarf novae. And since coming to GILA in 2019, he's been working primarily with me and Jason Dexter on a huge range of topics in accretion disks, particularly looking at situations where the magnetic field becomes really quite dominant in the dynamics of the disk. And he's going to discuss a number of aspects of that problem in his talk entitled Formation, Evolution, and Radiation of Magnetized Accretion Disks. Nico.
Cool. So thank you, Mitch, for the presentation and bringing me the opportunity to present this work in front of you. So most of what I will present has been done here at GILA. I think everything actually. And most of the stuff are not published yet, but I was really excited about presenting this result. So yeah. We'll be talking about the formation, evolution, and radiation of magnetized disk, and especially around black holes. So I will focus today on two types of accretion disk around black holes, even if I will speak mostly about X-ray binaries, but so AGNs, so active galactic nuclei, which are, yeah, sure.
It's the smiley face. No, on the right.
The smiley face. The smiley face is not.
We're on the smiley face.
Oh, we are?
Yeah, this is the spotlight to light
okay.
them up. There, that should be okay.
Yeah, so active galactic nuclei, which are accretion disks around the supermassive black holes, believed to be at the center of most galaxies, and X-ray binaries, which are binary system composed of a stellar mass black hole and a solar type star, whereas the solar type star actually feeds the black hole with matter, forming an accretion disk. So why do we study black hole accretion disk in the first place? So first, it's a very large source of high energy radiation in the universe, especially in X-rays and gamma rays. Then studying X-ray binaries and AGN actually gives a lot of, also TDEs, gives a lot of information about the black hole population. And we can measure stuff like mass and spin from these black hole populations, which are very valuable for black hole formation models. And then finally, AGN are believed to feed back on their environments, so their host galaxy or the clusters of galaxies that are nearby, through the ejection of matter. So it can be jets very fast collimated ejection, or it can be more massive, slower ejection called wind. And so all of this will feed back on the environment. And so if we want to understand how AGN and galaxy co-evolve, we need to understand what are the mechanisms producing those ejection and what are the cycles of life of AGNs. So just a little reminder of classical accretion disk theory for those where it's been a while. So we usually have this fundamental parameter of the accretion disk theory, which is the accretion rate, m dot, divided by the Eddington accretion rate. So the Eddington accretion rate is the maximum accretion rate where you can accrete before radiation pressure from the light that is emitted during the accretion actually prevent further accretion in. So it's kind of a theoretical maximum limit for the accretion. And so this little m dot kind of divides accretion disk theory into regimes. So you have a high m dot regime and a low m dot regime. And so in the high m dot regime, so you have your protons or your electrons. And so basically the plasma is very dense because you are accreting a lot. So what will happen is that, the electron and proton have very different roles. The electrons are the ones that radiate, because they are so light, they can radiate very easily. The protons do not radiate that easily, but the only way to radiate is by giving their energy to the electrons, but the protons are the ones that make the structure of the disk. So they are the one for the dynamics of the disk. So basically when the plasma is dense, what happens is that the electrons can cool very efficiently because they are mostly in an optically thick regime. So they can give their energy in radiation and leave out the disk. And the protons are also well coupled to the electrons through Coulomb coupling, so that the protons are able to give their energy to the electrons that are able to radiate that energy away. And so in the end, you end up with a relatively cold accretion disk that radiates its energy, that is geometrically thin and very luminous. On the contrary, in the low m dot regime, the plasma is not very dense. So that means that the electrons cannot cool very efficiently because they are likely to be in an optically thin regime. And then the protons are also not able to give their energy to the electrons, which cannot radiate anyway. But that turns out to give a hot, puffy disk that has a lot of thermal energy that it cannot radiate. And so it's not very luminous. So that's a classical picture of accretion disk theory. And we kind of divide low luminosity sources like X-ray binaries or AGN, like Sagittarius A star, M87, on this low m dot side, while high luminosity objects are on the high m dot. And so we expect the structure to be very different in both cases. So in this case, m dot is really the main parameter. However, there is a problem with that classification, is that if you look at, this is a spectrum of one X-ray binaries at two different times. And you see two very different spectrum, spectrum dominated by 1 keV emission, which is called the soft state, and a spectrum dominated by 100 keV emission, which is called the hard state. And X-ray binaries at high luminosity switch between those two states. So the soft state here can actually be well modeled by a thin disk, high m dot classical disk theory picture. However, the hard state cannot, because you need gas that is much hotter than in the soft states. You need a factor of 100 here. So that means that somehow you have hot plasma still around here, and like most of the emission is coming from this hot plasma. And yeah, the classical model cannot account for that. It is exactly the same for AGN. For example, AGN, according to standard theory, should emit mostly in the UVs. However, most AGN are very powerful emitter in the X-rays, for example, here. And standard theory cannot explain either why this happens. And even at low m dot, there is some issues. So we have a we have not the same number of sources at high m dot at low m dot because it's hard to observe sources at low luminosity. But so, for example, this is a spectrum of Sagittarius A stars, a supermassive center at center of galaxy, supermassive black hole at center of galaxy. And you have here the level of X-ray inquiescence, which you see is well reproduced by this dashed line, which is a standard accretion disk model at low m dot. However, you also have Sagittarius A star also have flares a few times a day, whereas the X-ray emission can increase by a factor of as much of 100. And in this case, you cannot reproduce that amount of X-ray just by invoking some standard model. So there should be something else happening there. And what I will try to argue today is that if we actually take into account the second parameter of the accretion disk theory, the magnetic field, we could maybe be able to explain all of that phenomenology. So if you put some vertical magnetic field inside the disk, what will happen to the disk? So the first thing that most of you know maybe is that you will create turbulence through the magnetorotational instability. So it's just an instability that develops even when you have a weak magnetic field. And so this MRI, the magnetorotational instability, will lead to accretion, dissipation of energy in the disk, and so provide all that you need for standard accretion theory. However, it's not the whole picture. So for example, the magnetic field will also produce strong magnetized jets that comes from the black holes through the Blanford-Snellick process. And these jets can explain what we see from X-ray binaries or AGN. You will also have slower, more massive ejections called winds that come from the accretion disk. And these winds, actually, this magnetized wind, don't only eject matter, they also induce accretion, and this on a shorter time scale than the turbulence does. So there is some pretty nice interplay there. And finally, you have the possibility to excite many microphysical instabilities when you have a strong magnetic field that could produce high energy electrons and so produce non-thermal emission, which will drastically affect the emission we see from those disks and make huge deviation from standard theory. So the thing is that the importance of this turbulence, these jets, winds, and non-thermal emission all depends on the strength of the magnetic field. And this is something that we don't know. We don't have a measurement of magnetic field from accretion disk. So what we can do is actually try to rely on theoretical model of that and compare to observations. So the picture now is that when you have a weakly magnetized disk, the only effect of the magnetic field is to produce turbulence. And so you are kind of in the classical accretion disk theory. However, when the magnetic field becomes stronger, you have huge deviation from that. So you can see here, for example, in this sketch, you have a accretion in elevated layers. So out of the midplane, the disk is much more puffed up than it should be from classical accretion disk theory. And so all of this will change the dynamical evolution and the appearance of this disk. And if you go to even more strongly magnetized disk, you arrive at the point where you are in the case of the magnetically arrested disk. So we'll talk a lot about that. So this is called a MAD, for magnetically arrested disk. And it is the most magnetized disk you can imagine. So if you put more magnetic field will just go away. And yeah, so I will talk mostly about that today, not so much about those, because they are the most interesting. And a very nice thing about this MAD is, so this is a magnetic flux on the black hole as a function of time. So you put some magnetic flux in your disk. What a MAD will do is that the magnetic field will just increase until it reaches a saturation point. And here you have this kind of cycles where the magnetic field actually is exposed and then goes in again, but it always saturates around this value. And this is very convenient for us to do simulations, because then you have a state that doesn't depend on initial condition. You put some magnetic field and your disk will just adapt and go to this saturated state by itself. So it's not, the result is not a product of what you put, it just, it is. And also observationally, MADs could be actually favored by polarization measurement of M87 and Sagittarius A star. So models of polarization actually suggest that you have a very strong magnetic field in those disks. So they could be very astrophysically relevant. So now the question is, how ubiquitous are MADs? So basically what we know, yeah, so that's the first chapter, like formation of MAD. So that will depend on the processes of magnetic flux advection and diffusion. So basically in an accretion disk, you have two different effects. You have your magnetic field lines here, you have some accretion. The accretion will bring the magnetic field lines in. But you also have another effect, that is these magnetic field lines don't like to be bent, and they can diffuse because you have some turbulent resistivity in the disk. And this will tend to for the magnetic field lines to be diffused outward. So you have really this competition between these two effects, the advection and the diffusion of the field. And whether or not you end up in a MAD state will depend on the competition of these two effects. So again, from standard theory, what we know is that if you have a thick disk, the length on which the magnetic field lines are bent is bigger. You don't have a big gradient in the field. So that means that the diffusion will be lower for this case, for a thick disk. However, in the thin disk, you see that theoretically, the field lines should be bent on a very small vertical extent. So you have a huge gradient that will easily diffuse through the disk. And that led like people to believe or think or whatever, but to think that thin disk should be weakly magnetized because they cannot hold on such a strong magnetic field, while thick disks should always be magnetized. So to test that, what I did is that I did a series of 3 numerical simulations where I changed the scale height of the disk. So I manually changed the scale height, the thermal scale height of the disk, and to go from the regime of thick disk with h over of 0.3 to the regime of thin disk with h over of 0.03. And so what you see here is a magnetic flux on the black hole normalized by mass transition rate. But so you see at the beginning it increased. And so let's look at the blue line, for example. This is kind of the classical case. The magnetic field increase and then it kind of saturates around this value where you are in the MAD state. And this is something that has been seen in simulation for 20 years now, or 10 years now, that hot, puffy disk always advex the magnetic field. This is the same for h over of 0.1. However, if you go to h over of 0.03, you see that, well, this happens too, but you saturate at a much lower value, but you do saturate to some values of magnetic flux. So you do end up in a MAD. You can stay in this state. So you can, even in this thin disk case, you can also end up in a magnetically arrested disk. And so this is Mostly due, we think, because the structure of the disk is very different from what we have in classical accretion disk theory again. So this is density, and this is radial velocity. Blue is inward, and red is outward. And so what you see here for h of 0.3, well, you don't see much, just that the disk is puffy and everything. But if you go to h of 0.1, for example, you have a huge deviation from classical theory, where actually you have accretion not in this 0.1 region, which is the two white lines, but actually above that region, where the magnetic field line pinch inwards, and you have very rapid accretion, much rapid than you would expect above this. And so this is exactly the same in the h of 0.03 case. And moreover, the 0.03 case is much puffier than you would expect. And we believe that all of these are what makes you able to actually go to a mad state, or to advect the magnetic field very efficiently, even when you are in a thin disk regime. And so this means that from a theoretical point of view, all this may end up mad. If you put some magnetic field in the disk, it will advect inwards through the black hole, and you will end up in that state. So this really motivates like this to study the radiative signatures of MAD, because we need to know what they look like if you want to actually see them. So first, I will talk only about the thermal emission. By thermal emission, it just means that the distribution of particles I'm considering inside the disk is purely thermal. So there is not non-thermal particles in this case. And so let's go back to this picture of X-ray binaries. So X-ray binaries alternate between these two spectral states. And so the stuff state is interpreted as black body emission from a thin disk. And the hard states should come from inverse Compton scattering of photons on some hot plasma. The question is, what is this hot plasma and where it is? And another thing about X-ray binaries, which is really interesting, is that they actually have a very complicated evolutionary track. So if you look at the luminosity of X-ray binaries during the eruption as a function of hardness ratio. So the hardness ratio is the amount of hard X-rays divided by soft X-rays. When you're on the right, you're on the hard state, and on the left, you're on the soft state. So X-ray binaries start in quiescence in the hard state, and then their luminosity increase. They stay in the hard state until some critical m dot, where they actually go to a soft state. And then their luminosity decrease again, and they go back somehow to the hard state before going back to quiescence. And so the reason why they do this track is not understood. What is this is not really understood. And like, why do they come back here? None of this is really understood. And what I will show is that actually MADS could give us some answer about that. So the idea here is that, from what I said at the beginning, you have this hot puffy disk. You cannot just extrapolate that to very high luminosity, because at some point you become too dense. And so the gas, electron and ions are coupled, the electrons are able to radiate, and you should collapse to a thin disk. But what if MADS with very huge magnetic pressure could actually support the disk structure to very large luminosity? So that was the idea that we had. And so to do that, we did a series of simulation, geometry simulation with eBlight, which is a radiative code. And so eBlight is a very nice code because it tracks individual photons and resolve absorption, emission, scattering events. So it's kind of the most complicated type of radiative transfer you could think of. It takes into account frequency dependent, non-local radiative effects. So it's perfect to resolve the inverse Compton scattering that is supposed to give this hard state. And also eBlight uses two temperatures for the electrons and protons so that you can capture most of the physics in that case. So what we did, well, what Jason did is that it is a series of geometry simulation with that, with different accretion rates. So one with 10⁻⁵, 10⁻⁴, 10⁻³ Eddington, roughly. And you see that as you go to higher m dot, you actually go to a much harder spectrum, which could kind of explain what we see in the hard state. This is this inverted power law that we see in the hard state. However, this is still at pretty relatively low luminosity of 10⁻² Eddington. So we are still not exactly where we want to be, which is, so we are here, we'd like to be there. So what happens if you go to higher accretion rate? Well, what happens is that you will collapse. So this is a gas temperature as a function of radius. And so from red to blue, it's time. So this is the initial time. And so what Jason did is that it he increased the accretion rate a little compared to the last stable state. And what you see is that as soon as you increase the accretion rate, what will happen is that protons will give their energy to electron, which will radiate, and the whole flow collapse to something that is kind of a thin disk or thinner disk. And so the hot gas kind of disappear, and we cannot follow the evolution of that anymore. And the reason why we can follow the evolution is because, as I said, deep light is very nice because it tracks individual photons, but that's become really hard when you go into the optically thick regime. Then you have a lot of those events and you cannot follow the evolution of those photons. But that doesn't mean that something unphysical is happening. It's just a limitation of our numerical code. And so in this case, we can try to study what happens after the collapse, but then we need another method. And so what I did is that I ran simulation with an artificial cooling function to control the temperature, like I did in the beginning for the formation of MADS things. And so in this case, we can actually study what's happening here where you are in the optically thick regime because you use this artificial cooling function. So this is again 3 simulation, MADS simulation with different h/r for 0.3, 0.1, 0.3. And in dashed is the expected density profile that you would expect. And in solid line is the measured density profile from the simulation. And so what you see is that at h/r of 0.3 and 0.1, you are very close to what you expect from standard theory. But as you go to h/r of 0.03, you have something that is radically different. The density structure is much wider, much puffed up. And this is because magnetic pressure becomes a very important factor inside for the vertical equilibrium. Those are dominated by thermal pressure. This is completely dominated by magnetic pressure in the vertical direction that is setting up the structure of the disk. And this gets even more interesting is that now you can look at the dissipation rate inside the simulation, because in the hot state, basically you need a lot of dissipation of energy into regions which are optically thin to produce this hard Comptonized emission. And what you see here in solid line again is the measured dissipation rate compared to the expected dissipation rate. And 0.3 and 0.1 are kind of in agreement with standard theory, but as you go to 0.03, again, this is much wider, and you have a lot of dissipation that is actually outside of the core, like the very dense core that you would expect from standard thin disk theory. So this is very exciting because that much dissipation outside of this very dense core could actually explain the high hard state. So what we need to do now is kind of to extrapolate that, because this is artificial cooling function. I'm not doing a spectra from that, but I can try to have an idea of what would happen if I had radiative transfer. And what I can do now is just, so GRMG simulations are dimensionless. They don't care about like the mass of the black hole or the accretion rate, as long as you don't put radiative transfer. But so what I did is that I rescaled my simulation to different accretion rate to try to go to this high state. And I think it's an okay approximation because, again, you are dominated by magnetic pressure. Usually this is not, because you change m dot, you will change the structure of the disk, and you cannot say anything about your simulation if you just rescale. But here, magnetic field is what is setting the structure. So this should be okay because, yeah, this doesn't depend on m dot anymore. So this is my simulation with the y Compton parameter, but don't really look at that actually, for 10⁻² Eddington rate. And so the blue line here is the zone where the cooling is larger than the heating. So that's the zone that will cool down. The red line here is the zone where 50% of the heating, the dissipation of energy is happening. So you see that at 10⁻² Eddington, which is already larger than what we did before, most of the dissipation is actually happening in a zone that will not cool down. So this should produce a very hot state. And again, you can extrapolate to even larger accretion rate. And so what you see now is that this zone, the blue zone where cooling is larger than heating, increased, but still, like there is almost 50% of the dissipation that is outside of this zone, which will cool down. So you still have plenty of energy to dissipate in these zones, which are optically thin and can produce a hard state Comptonized emission. So really, like the takeaway is there is a central core that will collapse, but you can still have that corona that can stay hot. So basically what we did is that we started from here and then we went from here. So the core collapsed, but you still have plenty of emission of dissipation inside that. And this could really explain what we see. However, at some point, sure, you increase m dot, then everything will cool. This blue line will go everywhere. And so you will transit to the substate. So that's for that part. Now we can do exactly the same here. So what I did before is that I rescaled my simulation to a temperature of like 10 to the 9 Kelvin, like in the hard state. Now I can do exactly the same and scale my temperature to a temperature of 10 to the 7 Kelvin, which is typical of the substate. And we can see what happens. And this is very interesting because it is not clear why X-ray binaries go back there. So from standard theory, you have no reason to go back there. This solution, the SynDis solution, is a valid solution up to very low, down to very low luminosity. So if you decrease m dot, logically what should happen is that you just stay in the substate to very low m dot. And at some point you will go back there, but at very low m dot. So why do you go there is a real question. And again, we can address that question now. So starting from here, I rescale my simulation to the substate. I'm starting with high accretion rate. And the black line is the zone where I'm effectively optically thick. Inside that zone, I'm effectively optically thick, so I'm able to cool down. Outside, I'm not able, so I will stay whatever. But so you see that as you go to 10⁻² Eddington now, you are not optically thick anymore. You are optically thin everywhere. So that means that this disk has no way, this gas has no way to cool down. So it will puff up and go back to a hot disk. And so that gives a very nice way to actually transit from the soft state to the hard state in this regime. So, so now that I've talked about the thermal emission, let me talk about the non-thermal emission. And again, non-thermal meaning non-thermal particles. So let me go back to the saturation mechanism in MAD. So you have like, okay, you saturate around this value, but you saturate by having this kind of eruption, like sawtooth feature. And the way it happens is basically that you have all these magnetic fields on the black holes. And at some point, it reaches saturation, and the jet is so strong that it will actually give back its magnetic field to the disk. And what will happen in this case is you create this very low density cavity that has a very high magnetization and take all the magnetic field away outside in the disk. And after that, you know, like the accretion will go on again. And so you have the magnetic field will build up again until you have, again, this kind of eruption that takes the magnetic flux away. And this very time-dependent feature is very interesting because it can actually accelerate particles to very high energies. So what happened in this low-density bubble is that you have a very strong reconnecting current sheet. So a current sheet is a zone where the magnetic field reverses its polarity. So the blue and red are two different polarities of magnetic field. And in this current sheet, you dissipate a lot of magnetic energy, and you can possibly dissipate that energy into non-thermal electrons. So what I did is that from this geometry simulation, I identified all the current sheet that I have, and from this current sheet, retrieve their properties. So like, for example, the magnetization, temperature, everything that is important to know about a current sheet. And then I use prescription from particles in cell simulations, which are simulations that can evolve the individual trajectory of particles and are used to study microphysical plasma instabilities. And so from these studies of reconnection, I can assign a non-thermal particle distribution at each cell of my simulation according to the properties of my current sheet. And from that, I can actually compute the non-thermal X-ray emission that I should see. So this is for Sagittarius A star that I did this study. And so from that, by summing on all the cells of my simulation, I can actually produce a spectra of Sagittarius A star. And so you have in black the mean spectrum. In gray, here's at the minimum and maximum in X-rays. And here you have the points of observations. And here is the maximum X-ray flux observed. Here is a minimum X-ray flux observed. And here is a median one. And the gray shaded region is the zone of variability inside my simulation. And you see that thanks to this very time-dependent feature of the expulsion of field from the MAD, you can actually produce a great deal of variability in the X-rays. It's actually okay that here we are below this value because we expect this value to come from further out in the disk. So yeah. And you can actually also produce light curves from that. So Sagittarius A star has flares every like twice a day or something like that in average. And you see that you have very strong spikes in X-rays and infrared, like kind of what is observed in Sagittarius A star again, with simultaneous X-rays and infrared flares. Sorry, that's my simulation. All is that in my simulation. Yeah, I didn't put the. Yeah, and this is X-rays and this is infrared. And so finally, I actually have plenty of time. Okay. Finally, I want to talk about like what non-thermal particles could do for X-ray binaries. So I went on Sagittarius A star. Let me go back to X-ray binaries. So even in the soft state, so I was talking a lot about the high hard state, but even in the soft state, it's not really, everything is not clear. So you have this non-thermal parallel tail here that extend from like around 10 keV to MeVs. And it's really not clear where is that coming from because it shouldn't be coming from a standard thin disk. And so what we wanted to know is, yeah, can we actually come up with a model from that based on what I did for Sagittarius A star? And the thing is that in the soft states, you have a very dense collisional optically thick disk. So even if you accelerate non-thermal particles, they will collision with ions or other electrons and they will actually thermalize. And they could actually thermalize by radiation too. But so in this configuration, where would actually non-thermal particles come from? And we had the idea that maybe they could actually come from the ISCO, which is the innermost stable orbit. So there is a radius in general relativity where past this radius, there is no stable orbit anymore around the black hole. So that the disk will just infall at a much larger rate than it does outside the ISCO. So in this region, you have faster inflow. That means that you have density that it's much less. And so you are less collisional. And so this zone is actually a great potentially great place to look for non-thermal particles. And because it is less dense, it might be actually optically thin. It might actually, ions and electrons might decouple so that this region could actually puff up. So what we did is that we assumed that this region could puff up and we can verify that if it's puffed up, it can actually stay puffed up. And from that, we computed the non-thermal electron properties of that zone. And so this is a work that Leah did actually here. And so what she did is that she used a 1D dynamical model for the plunging region. And on top of that, she used a prescription from peak to estimate the reconnection properties of these particles, like I did in Sagittarius A star, and computed a relative model, like a multi-zone relative model. And she could find like a spectrum from that. And so here you have the disk spectrum, which is coming from the optically thick, geometrically thin accretion disk. Here you have the thermal plunging region, the electrons that are thermal in the plunging region. And here you have the emission from the non-thermal particles, which are in the plunging region. And you see that you can have something that looks very like non-thermal parallel with an energy in the non-thermal parallel that is a few % of what's in the disk, like we observe. So again, this requires very strongly magnetized disk in the first place because you need very high magnetization to be able to accelerate those particles. And yeah, so I think I'm done. So I will just conclude here. Magnetic fields. Yeah, I just want you to take away that basically accretion rate is not the only parameter of the accretion disk theory. You can do a great deal with a magnetic field. So it can greatly impact the evolution and relative structure of accretion disk. I did not talk so much about the evolution, but there is a lot to say. MAD are also likely to form in accretion disk at different luminosity, so from very low accretion rate to high accretion rate. So they could be kind of everywhere. And yeah, MADs can be very bright even when hot. I didn't talk about that so much, but The vertical of SIN-MAD is set by the magnetic field. And as we saw, this could kind of explain the hysteresis of X-ray binaries, because then you can have a lot of dissipation outside of what you would expect to be a thermal, very dense core. And also, strong magnetic field now can enable the production of very high energy particles. And that could explain the X-ray flaring of Sagittarius A star, for example, the power latte in X-ray binaries. So thank you very much. Yeah.
We have some time for questions.
I didn't clearly understand what the relationship was between the rate and the circulation. So, for example, in this case, you say you fix the magnetic field saturation by tension of the people like
Okay, so is the question, does the saturation of magnetic field depend on m dot? Or yeah. Yeah, so it does. And so from here, for example, you see like the saturation value, which is just the saturation value on the black hole, but it also reflects inside the disk, actually depends on the h/r. And h/r is basically a proxy for m dot. Being at small h/r means that you are at high m dot. So this cannot hold a magnetic flux that is as large as in the case of a hot puffy disk at low accretion rate. But this doesn't mean that the disk will be less magnetized. So for example, in this case, I did not talk about that, but I found that the magnetic field in the disk, as I change h/r, actually stays kind of the same inside the disk. And because you decrease the thermal pressure, that means that it's actually more and more magnetized as you go to higher and higher m dot. Yeah, so that's the magnetic flux on the black hole here, divided by the accretion rate, but that's just a normalization factor. But so yeah, it's the amount of magnetic flux you have on the black hole here.
Hi, I'm Yuta Notsu from Raspen NSO. I have a question about flare-like light curve in later part of the slide.
Of Sagittarius A star?
Yeah. No, in high energy particle part.
Oh, yeah.
Yeah. So yeah, I'm studying stellar flares actually, and often we plot a flare frequency distribution from this kind of light curve shape. And are there any information on frequency of this kind of flares from? Are there any information from this frequency of flares on parameters of magnetic field or physical parameters?
Yeah. So the question is, right, is there like a characteristic frequency for those flares based on some physical mechanism?
Yeah.
Yeah. So this is actually related to the question before. Well, you saw the eruption of the flux. Well, those happen at the same time as the eruption of the flux. And this happens kind of periodically, although you would have a very low, periodicity. I mean, it wouldn't be exactly periodic. It would give you something, a very broad, for example, peak in a Fourier range. So this is not exactly periodic, but this happens at something that we can predict to be, I think 1,000 RGC or something like that. And this is really related to the magnetic flux eruption from the black hole. So yeah.
Can we compare with the observational data of X-ray light cover?
Yeah, so I don't have here on this plot the observational data, but basically here you have a hours scale for Sagittarius A star, and Sagittarius A star shows that like twice a day or something like that. So it's kind of consistent with what we see. I mean here, yeah, or here.
Okay, thank you.
Do you know if there's anything on chat? You want, yeah, Andrew.
You talked about both X-ray binaries and supermassive black holes, and they kind of smush from one to another. They're all described by the same physics. I mean, is that surprising, or is that true?
Yeah, when we come to radiative transfer, for example, there is distinctions between the two. But yeah, I agree. For example, this mechanism, you should actually expect that if you have MADs in X-ray binaries, you should expect to see that. The thing is that, for example, Sagittarius A star, we can observe it at very low luminosity because it's very close. X-ray binaries, we don't have good data for X-ray binaries at this very low luminosity. So even if we can see that, it's not clear that, well, we can observe an X-ray binary that's this kind of physical range. It's not clear that we would see this signal. And they evolve much faster. So you would see that like as a millisecond pulsation or something like that. But still, we could, if we had the sensitivity, we could observe that. And yeah.
Anything on chat?
Maybe, but not yet.
Yeah.
Okay, I'm gonna ask about the hysteresis. So you said you can explain the transition from hard to soft state at a high m dot by just the disk collapsing, right? Can you estimate the time scale for that? And does it work out to the right time scale that we see, which is extremely long?
Yeah, so basically the idea is that here you transit from the hard state to the soft state because your density increase, you become more optically thick in more regions, and so you cool down more. But so everything is driven by the change in the accretion rate because the density is driven by the change in the accretion rate. So cooling is very fast. You will cool immediately, but how much of the disk will cool depends on the density structure. And this depends on the value of the accretion rate. And it depends on how the accretion rate evolves at larger radii. And this is something that is really not clear. So for example, the simulation I showed, they only study what's happening inside the between 10 and 100 Rg. Here we are talking about what's happening at 10 to the 4 Rg, 10 to the 5 Rg. So this is really out of the scope of the simulation. However, yeah, we have some ideas of, there could be some thermal viscous instability inside X-ray binaries at the larger radii that could give the time scale of weeks or something like that to transit from this to this. But it's really dominated by the physics at the outer scale. It's not about something we can say in the simulation. And it's not about cooling. Cooling will happen instantaneously for an X-ray binaries like compared.
This is another question from a solar physicist, and you'll understand why. Do the jets favor a particular disk configuration, and turning that around, what can the jets tell you about the magnetic configuration or magnetic state of the disk?
Yeah, so very good question. Actually, jets kind of favor very magnetized disk because that's kind of the only way to produce this fast collimated jet that we observe in AGN and XRBs. So actually, to have the efficiencies that observation require, you kind of need a MAD state. And so that's another big point towards like having a MAD state in disk. However, for example, there is also, so this line here is showing, here there is a jet, and here we don't observe a jet. So for example, in my model, it's not really clear that what would happen to the jet, because if I'm MAD all the way, then you should see the jet all the time, while we don't see the jet in the soft state. So either it's that the jet is not here because the magnetic field structure has changed, or it's because the jet is actually less efficient in a thin disk. That could also be a possibility. But yeah, short answer, strong magnetic fields are required to launch jets, and MADs could provide that. However, sometimes you don't need a jet also. And sometimes, for example, in quasar, you need very high luminosity. So you are in the kind of soft state regime, but you also have a jet. So yeah. I don't know. Yeah, I know.
There's two questions on Zoom. First from Yuri Tumra. Could you restate again how the magnetic fields are built that are present in the disks? Any induction proceeding there or mostly from the jets?
Okay. So the magnetic fields in the simulation are put in at the beginning in the simulation. Then they advect inwards, or they could diffuse outwards, but in fact, they do advect inward. So they are really magnetic fields that was put as an initial condition and then advected inside the disk. In reality, this could come from, for example, in X-ray binaries, a stellar companion has a very strong magnetic field, has a lot of magnetic field to give. So this could actually be magnetic fields coming from the outer part of the disk that is brought inward and end up on the black hole. So it ends up on the black hole, it does not start on the black hole. In AGN, for example, it could also be just the environment, like molecular clouds or whatever. And there could be some dynamo also processes inside the disk. However, I'm not sure that's really clear. And yeah, what would be the effect of dynamo? Yeah.
The second one is kind of unrelated to your paper, but Kishmia Nandu asks, what is the most challenging and most rewarding parts of your academic and research career so far?
Yeah, I don't know. Working with Mitch. What? Oh yeah, yeah. Oysters at Jack Fisher's house. Yeah.
Okay. Any other questions? I have a question.
Yeah.
Or you guys keep talking to the chat.
You talked about the importance of having a net magnetic flux embedded in the black hole. Have you given any thought to what might happen if that suddenly disappeared or flipped?
Okay. You want to do some advertisement for?
Yeah.
Yeah, sure. I have gave thought about that. Yeah. So if the magnetic field actually switch polarity for, imagine you have a mat state, and suddenly, like the magnetic field that is brought from outwards, it just of a different polarity. What will happen is that the other polarity will reconnect with the existing polarity and just destroy the mat state gradually. And so in this case, you can have very interesting events. So for example, if you say that X-rays are due to the fact that you are magnetized in AGNs because you have dissipation outside of these layers, and UV are coming just from the accretion rate, like the disk. So if you cancel the magnetic field by advecting the other polarity, you would cancel the X-ray without canceling the UV, for example. And that's a model we put forward with Mitch to explain some very drastic changing look AGN, which have a very large dip in the X-ray, where the X-ray is shut down by 3 orders of magnitude, while the UV doesn't change almost, which is kind of hard to explain with just a change in accretion rate. And yeah, you want to advertise the NASA press release also?
I'm surprised you don't have our cartoon.
Yeah, because I said I was short on time. Actually, I'm super large on time. Okay.
So yeah, so group from Goddard claims to have some evidence for this process, which is going to be the topic of a press release in 3 weeks. Anyway, yeah, yeah. Hi, Larry.
Yeah, I was wondering, you're saying that within the ISCO, you expect that to be puffed up. So does that have any implications for any other processes that are happening? Does that affect what we would expect the accretion to look like, or what does that imply?
Yeah, so, well, first it could just produce a region where you have a very highly energetic particles that just produce non-thermal emission. And then it could also produce affect like the jet physics, because the jet is coming from the base of the black hole. And if you have a puffed up disk near that, that could actually change some of these. Leah will actually be studying that. So, yeah.
Is it on? Yeah. Okay. Yeah. How important are winds in these simulations versus jets?
Yeah. So from my experience, at least, winds are not that important in the sense of like amount of powers that go into the wind. It's not that they are more powerful than jets, but they do have a big influence on the accretion. So as I said at the beginning, but again, I removed all of that because I thought I was short on time, but winds can produce accretion on faster timescales than turbulence does. And so for the same accretion rate, if you have a faster inflow speed, that means you have a lower density. So the winds, for example, can produce a very different dynamics inside the disk. They can produce like lower density region, faster changes inside the disk, all of this stuff. So yeah, and it could have a very big importance to explain like dynamical events that we see. So either the extra binary hysteresis, or even like changing look AGN, which switch from one state to the other states in months or years, where this will actually change in I don't know, million of years, or not million of years, but very long time scales. And so wind could actually play a role in that.
Any other questions? Not, let's thank Nico.